I did not realize that's like
So welcome everybody to lecture 6 in CS267. And I'm Jim Demmel, and I'm going to be happy to give you the next 2 lectures on sources of parallelism in locality. So you've been told, obviously you've signed up for the class because you know parallelism is important, finding lots of independent things to do at the same time. And I'm sure you've been told, and you'll be told many more times, that one of the most expensive operations a computer does is moving data. And so that means it's also important to organize your parallel computation so there's lots of locality in it, that you're doing all your work on local data. And the good news is that real-world problems that come up that you want to simulate very naturally have both parallelism and locality in them. And so you should recognize those patterns, and that's what this lecture is about, recognizing those patterns and see, oh, I know how to solve that problem. So what are the patterns that come up over and over again? Many objects operate independently of others, so hopefully all your brains are processing the words I'm saying independently of one another. And then there's balls bouncing around on a billiard table or rolling around, F equals ma independently. Then it's also true that objects depend much more on nearby objects than more distant ones. Again, billiard balls are pretty natural. Until they actually get close enough to collide, they don't affect one another at all. But it's also true, say, in gravity, that distant objects are going to be, have less effect or a simpler effect on an object moving under gravity than the nearby ones. And the dependence that you have on distant objects can often be simplified. So actually gravity, objects moving under gravity is an example of both, of all 3 of these things. So you have a force in an object, it's kind of moving independently of all the others. It certainly depends on close objects, so the moon depends more on where the Earth is than where on, say, the Andromeda galaxy is. But the other thing is that we can actually use this idea that far away things can get simpler in a very striking way. So for example, suppose you wanted to compute the gravitational force on the Earth, so you walk out at night and you look up at the sky, and you see about 1 billion little white dots, and you say, oh, I guess I need to sum 1 billion numbers in my program. And then you realize one of those little white dots is the Andromeda galaxy. And it consists of another little billion white dots. And suddenly you start to get worried about how much work there is to do. But your first impression was just fine. The Andromeda galaxy is well approximated by a little white dot, with a total mass and center of gravity in the right place. And that'll give you all the decimal places that you need to get the force of gravity on Earth. And conversely, if you're in the Andromeda galaxy, the Milky Way looks like a little white dot. And if you use that idea recursively and break things down so our solar system looks like a little white dot and so forth inside the Milky Way, then you can get the cost of computing all the gravitational forces or electrostatic forces or other forces on n objects down from order n squared to order n. And that is, it was a real mathematical breakthrough and has won many prizes. And so we will be talking about that and how it generalizes well beyond gravity and electrostatics as well. So the other thing is that when you make a model of a very complicated system, in order to actually have a reasonable program to simulate it, that can introduce even more parallelism. And so when you take a continuous problem, things moving continuously over time, you have to discretize it. You're only going to know where let's say the billiard balls are at time t equals 1, t equals 2, t equals 3. That actually simplifies the dependencies, because you're only going, what happens at time t is only going to depend on what happened maybe at time t minus 1 or t minus 2. You don't have to look at all the different data that you have. And it also means that if you have to ask, is there a collision, who's nearby, there's only a limited number of other things that you have to look at. And so we're going to take advantage of all these things and look at examples. And I should say that in the real world, you may have multiple levels of parallelism, because you're going to have some sort of scaled simulation. Okay. So here are the basic kinds of parallelism we're going to talk about, and they're going to be sorted in order from the most discrete to the most continuous. So in the most discrete case, everything is discrete. You have a finite number of variables. They only, have maybe a finite number of values. They exist only at finite time steps, and there are a lot of examples like that. So in the 1960s in Scientific American, they had this thing called the game of life, where you have a square grid. Each square in the grid is either dead or alive. You just look at your 8 nearest neighbors and decide, am I dead or alive on the next time step? So that's a simple example we'll use to illustrate things. But manufacturing systems, where is the object on an assembly line? At what stage is it? What's being done to it at that time? Finance, all sorts of transactions happen, and that's a discrete system. Now, circuits, especially if you think of a digital computer, right? At every time step, you're either going to switch from a bit equals 1 to bit equals 0. That's also a discrete system, and that can be modeled at many levels. And then we'll also use a sequence of computer games to illustrate this. So a very ancient, simple game at this level was Pac-Man. Okay, everything's discrete. So the next level up, where I'm going to make things a little bit more continuous, are particle systems. So it's discrete in the sense I have a discrete number of particles, but now they are moving continuously in time. And so billiard balls, I mentioned before, galaxies moving around under gravity, atoms if you're doing some sort of molecular dynamic simulation. Circuits again, and in this case, you could be talking about moving electrons around independently. That's a much more detailed level of simulation. And then pinball, a slightly more advanced game. So let's make things just a little bit more continuous. And now we're going to have a finite number of lumped variables that depend on some continuous parameters and a few of their neighbors. And this is also known as solving ordinary differential equations. You have a finite list of variables that are a function of time and depend on a few of the other ones. And so in addition to that, you may have some algebraic constraints on them. If you're a double E, you might think, oh, Kirchhoff's laws, something like that. So it's not just differential equations, you may have algebraic equations too. And this comes up, for example, if you're in the civil engineering in structural mechanics and you're trying to write down a model of how a building sways in an earthquake. This is a natural thing to do. Chemical kinetics, you write down how the concentrations of certain species change over time. Circuits again, there's a program that's widely used in Silicon Valley and everywhere else called SPICE that was invented here a long time ago by Don Peterson, and it precisely uses this sort of model to model circuits. And then a slightly more advanced game, which I'll show you a video of later, Star Wars, The Force Unleashed, which does real-time finite element simulation in parallel so that when Darth Vader smashes something, you get a nice realistic effect. And then the most continuous thing of all is where everything is continuous. The variables depend continuously on time and space and maybe other parameters, and this is more generally known as solving partial differential equations. So the heat equation, temperature is a function of time and space, elasticity, motion, effect of a material that's moving around and deforming, electrostatics. Now finance again, you might say, what? Isn't that discrete? Well, this won a Nobel Prize. It's the Black-Scholes equations for derivative pricing, so people model it that way too. Circuits, you could potentially use the Schrodinger equation to figure out, what's the density of all the electrons, medical image analysis, and then one more slightly more advanced game, which is Terminator 3, The Rise of the Machines, where our former governor played a role. So I'd like to say these two things are different because this is sort of ODEs and this is PDEs. They're also different because this work was done at Berkeley and this work was done at Stanford. But what they have in common is they both won Academy Awards for technical achievement. And in fact, this one, the Stanford one, was Ron Fedko, and the Star Wars one was James O'Brien, and the official name of his prize was for finite element destruction modeling. So we'll see that video of that later. So, and a given phenomenon can be modeled at multiple levels. That's why I have finance and circuits and games and all of that appearing multiple times. And there's a link to the video, but I'll show it to you later. So since a lot of you are from EECS, let me just put all the different circuit examples on one slide, sorted in order from the most discrete to the most continuous. So these are all the different levels at which you could imagine simulating a circuit. Instructions, add these two numbers, load something from memory, down to the cycle level where you have individual functional units like ALUs, and you can go down to RTL where you have individual registers and counters, and down to the gates and switches. And by the time you get to this level in circuits, that's the ODEs, that SPICE runs. And then there's, if you actually want to know the density of all the electrons. So these are all used in practice at different levels, and you may have used them yourself. So just to summarize, here's what I'm going to talk about for the next 2 lectures, or at least lecture and a half. Discrete event systems, time and space are discrete. Particle systems, where it's discrete in the sense I have a finite number of particles, but now time is continuous and their locations are continuous. Then this you can think of as a special case of lumped systems or ODEs, where I can have kind of arbitrary continuous locations in time. And then PDEs, and I'll probably only get through the first 3 today, and I'll leave PDEs for next time. So in order to illustrate this, all these different models without you having to know the physics or whatever of every one of these different areas to make them realistic, we've built some toy problems and posted them on the CS260 webpage called Sharks and Fish. And we sort of made up some rules of physics which are interesting enough that the sharks and fish have some interesting behavior, but it's very simple to write down in a few lines of MATLAB. And so you have sharks and fish living in an ocean, and we have different rules, different examples of this. I'll list them on the next slide. They could be moving discretely on a grid or continuously in what is real water. There are rules for breeding, creating new fish, sharks eating fish, fish dying, forces in the ocean pushing them all around. And you can imagine that sharks are attracted to fish and fish are not attracted to sharks. So there are all these inter-fish forces and so forth. And we've made them available over time in many, many different languages. So depending on what your favorite programming language is, we haven't updated this for a while. So you can see some of these languages are a little bit old and dead, and we haven't bothered to do it in Python yet. So it could be updated. And some of the homework will be sort of based on these same kind of simulations. And so here are the 6 different flavors if you want to look at them. So you only have fish, and they move subject, they just swim around subject to an external current, Newton's laws, so everybody's independent, just moving F equals ma. Then fish like to form schools, so we add a little bit of gravity, so the fish come together and try to form pods or whatever they're called. Then there's a discrete version where it's really just the game of life, really, where each cell either has a fish in it or not, and they come and go discretely. We add a race condition to it so that if 2 fish want to simultaneously move into one cell, they can't because there's no room for them, so you have to deal with that race condition. Then we throw in the sharks, again in the discrete case, and if a shark and a fish move into one cell together, you can imagine what happens. And then finally there's a continuous version of that. Okay, so now any questions before we go on to discrete events? So these are represented by a finite set of variables. And if you take all the values of all the variables together in one big vector, say that's called the state of the system. And what you do is there's a formula called a transition function, so that each variable is updated by gathering some values of some of the other entries in the state vector, computing a function, and updating it. Now there are two kinds of systems, and these are going to have two different kinds of parallelizations. One is called synchronous, and the other is asynchronous. And the synchronous case is what we all think of as our computer doing. There's a global clock, and at every time step, you evaluate the transition function, and everybody changes at once. Now, we all thought this was how our computers work, but then we heard about all of these bugs like Spectre, so we know that there's a lot more continuous timing that can be used to hack. All the computers have been built for decades, but anyway, this is our model of a synchronous simulation. And then there's asynchronous, where the transition functions are only evaluated if the inputs change. And so you don't have to look at your neighbors at every time step. It's only when something occurs. So for example, if a cell in memory is not going to change every time step, it's only going to be when there a read or a write is applied to it, and that's a different kind of simulation. We're going to call that event-driven simulation. And the game of life works there too. And so I'm going to use that, excuse me, as an illustration to show you how this parallelization works, because the rules, the transition function is very simple. It's just a two-dimensional grid, and you look at your 8 nearest neighbors, and you decide what to do in the next time step. So here's how to think about it. We're going to have two-dimensional grids. I'm going to call one new and one old. And so in order to consistently move, take a step, what everybody's going to do is they're going to read the old data, that's not going to change, compute the transition function, and then write the array called new, right? So that way there won't be any race conditions where somebody writes the new data and you grab it and you should have grabbed the old data. And then you just ping pong, you reverse it, you read the new data and write back into the old, and that way you can consistently take time steps. So it doubles the memory, but it works just fine. So it's easy to imagine how to parallelize this. I'm just going to take my square domain and break it up into subsquares. So suppose I have 9 processors, P1 through P9. I'll just break up my big square where the game is going on into these 9 smaller ones. And here's going to be the code. I'm going to each processor is going to just update all the cells in which it knows the local data. So so what data does it need? Every cell looks at its 8 neighbors. It's 8 adjacent neighbors, up, down, left, right, in the 4 corners. So that means that as long as you're not on the boundary, that processor owns all the data that's necessary to compute the function. So the first step is update the local system where you know all the local data. So it's everybody except right on the boundary. Then you wait until everybody's done. You execute an instruction called a barrier, and that is a standard parallel subroutine where nobody's allowed to get past that line of code until everybody's gotten there. That's what the barrier does. Then what you need to do, finally, is communicate, move data, and everybody exchanges with their nearest neighbors just the data on the border. So processor 1 will send those numbers over to processor 2, processor 2 will send its numbers over there, and everybody exchanges with the, let's say 8, or however many neighbors you are, and then you have enough data to finish updating all the data on your borders, and then you just repeat until you've taken all the time steps you want. And so this is naturally parallel. It's perfectly load balanced, and it's doing a great job at locality because almost all the work is done on data that you own locally, and you're only going to send out a few guys around the border. Now, I chose squares here, and the question is, how in general do I pick the right shapes? Your intuition, that squares should work here is pretty good, but it isn't always this simple. So let me just, show some alternatives for that example, and then try to generalize it where you may have arbitrary kind of connections. So let's do the simple case. So I have an n by n graph, and I'm only connected, let's make it simple, with 4 nearest neighbors, north, south, east, and west. And so I'm going to give 2 possible partitions and ask, how do I quantitatively decide which one is better than the other? So suppose I have an 18 by 18 grid, and I want to assign that to 9 processors. What's the right way to do it? Well, one simple way to do it is just give every processor 2 adjacent rows. So the red processor gets the first 2, the blue processor gets the next 2. That's a very simple way, that's simpler than the one I had before. Here's the other way I was describing it in the last slide, where I divided up into subsquares. So the question is, how do I quantitatively compare those two and say which one is better than the other? What I'm going to do is count how much data I have to communicate. What data gets communicated every time there's a black edge that goes from one color to a different color, from one processor to a different processor, data has to move across that. So here I have n edges, there I have n edges, and so altogether I have n times p minus 1 edge crossings for that particular one. What about this one? You can do the counting, and because these things are squares, it's only proportional to the square root of the number of processors. And so that is asymptotically less communication. So what is the general philosophy that works beyond nice simple layouts like this? I'm trying to minimize the surface to volume ratio, if you like, of these partitions. And if I didn't give you any other constraints, what shape minimizes the surface to volume ratio in the plane? A circle, right. It's kind of hard to tile the plane with circles, right? So I have to make some compromises here, and squares are pretty good. But if I have kind of arbitrary connections, in some more complicated real-world simulation, I need to go beyond your geometric intuition. So let's talk about graphs. And graphs are the model I'm going to use to sort of solve the problem in its most generality. And I'm going to talk about this in the synchronous case. So think of a circuit, because a circuit is very naturally analogous to a graph. So a graph is a bunch of nodes connected by edges. That's the mathematical model. So in the case of a circuit, it's a bunch of sub-circuits connected by wires. Each wire corresponds to an edge. And edges, a bunch of wires can come together at one point. That's a node. So what is the data structure? It can be, you can have arbitrary wires going anywhere. You can have an arbitrary connection. So what I'd like to do is, and so here's an example, which is very small and regular. Each of these blue things is a vertex, and each of these edges is a wire connecting them. And so what I'd like to do is somehow assign all the work evaluating all the functions at those vertices to 4 processors. And so here are 2 natural ways to do it that you might do. When it's irregular, that's the hard problem. So what are my goals for, let's say, choosing that one over that one? Well, the first goal is to load balance. I want to give every processor an equal amount of work to do. And so that means that each of these partitions should have an equal number of vertices in it. And here they do. Everybody gets 2 vertices worth of work to do. So that's perfectly well load balanced. And the second goal is to minimize communication. And what is communication? Well, every time there's an edge connecting one vertex to another that goes from one processor to another, that's communication. So that's communication, but that one's not, because that's all on the same processor. So let me just count the number of edge crossings, and here it's 2 plus 2 plus 2, 6, and here it's as bad as possible. Every edge crosses, and so it's 10. And so the goal in general is you have an arbitrary graph. It has a bunch of vertices with a bunch of edges connecting them. And what I'd like to do is partition it into p different partitions. And here it's 4 partitions, but p in general, where each one has about an equal number of nodes, and I minimize the number of edge crossings. That is called the graph partitioning problem. And if you've taken a computer science class and studied it, you know it's NP complete. So to find the absolutely best way of doing this for an arbitrary graph. So how many people have heard of NP completeness? Okay, that means the best algorithms anybody's ever figured out, since this idea was introduced by Dick Karp, one of our faculty a long time ago. He invented NP completeness. It's exponential time, right? So much harder than the original problem you wanted to solve. And so the good news is that over time, people have built an enormous number of algorithms and software tools and packages that you can just call that are good approximations to solve this problem. So when you see this and realize you have to do it, you should say, oh, I'm just going to call this long list of software tools that you'll learn about in a later lecture. Okay, so that's synchronous circuit simulation. And as I said, we'll have a later lecture on graph partitioning, and both on interesting the algorithms themselves, and then on which tools implement them. So here is a a slightly different problem, which motivates the asynchronous case. So suppose this is what my problem looks like. I have some sharks, red, and some fish that are green, and there's these very weakly connected ponds, and I would still like to do this simulation as these move around and interact with their neighbors. And so if I had 3 processors, it would be natural to assign each of these ponds to one of the processors. But now the question is, how do I pass information along these different edges? So would I want to do the synchronous case? What would be wrong with having a global clock where at every time step I just say, is anybody there? Is anybody there? Is anybody there? Is anybody there? Almost never is there going to be somebody there that would affect me. So that would be a very, very slow simulation. So what I'd like to do is have an algorithm which just goes ahead and anyway. And so there are several ways of doing that, but in order to get the right answer, everybody that comes across that edge is going to have a timestamp. So I know when it was created, and I'm going to have to compare it to my timestamps to know, do they match? Right? So in order to keep it all consistent and correct, all the events in the system are going to have timestamps so that I can do this correctly. So the first bullet there is just what I said. If I just kept asking, for a global clock, I'd waste a lot of time. So instead, we're going to do something asynchronous. And so there's going to be no global time steps, but every individual event will have this timestamp, so I know, when I can use it. And the example on the last slide was this game of life in loosely connected ponds, but it also comes up naturally in circuit simulation. In that case, the events are gates changing. I don't want to, in my simulation, look at every gate on every cycle and ask whether it changes. I only want to, update a memory cell when something actually goes there. And it would come up in traffic simulation too. In that case, the events may be cars changing lanes or something like that. So it's going to, so this can be much, much more efficient than having a global time step, but it's going to be harder to parallelize. So and that's why there's more than one way to do it. No one is best. So let's suppose I had a distributed memory computer, so 3 processors, and the only way they could communicate with one another is over this network. And you've probably seen that picture before. So if you're writing code, you might write it in this language you'll learn more about later called MPI, where you have to do a subroutine to send a message and call a subroutine to receive a message from another processor. And so, so the question is, when should this guy ask, has any mail arrived from my neighbor, over the network? How does it do that in an efficient way? So, how do you know when to execute a receive? So there are going to be 2 ways of doing it, and they're called conservative and speculative. And so the idea of conservative simulation is that you get all this data from your neighbors, they all have timestamps, and you say, well, if all the data from my neighbors I know up to time t equals 10, I'm allowed to go simulate up to time t equals 10, but I can't go any farther. I have to wait till I get some more data. That's the conservative approach. The trouble with that is it can create deadlocks, because everybody's waiting for everybody else. I'll show you a picture of that next slide. So we need to have some deadlock detection and deadlock breaking algorithm to make that work. The other way of doing it is speculative. In that case, you just take a risk and keep on computing ahead. And so suppose you compute up to time t equals 10, and then suddenly you get a message from your neighbor about something changed at time t equals 5. What do? You have to back up and re-simulate. And so hopefully that won't happen very often, but it means you have to save the state. You can't just throw away old stuff. You have to keep some history and be willing to back up and compute. And there are examples. The first example, there's circuit simulators that do it the conservative way. There's circuit simulators that do it the other way. There is no one best way of doing it. It depends on your application, which one works best. And I should say in all of these things, if you're trying to do both good load balancing and optimize for locality, which has been our goal so far, that's particularly difficult. Because suppose I have only a part of my circuit that's active at one point, right? The ALU is really busy, but the memory isn't having much going on. How do I load balance that? So ideally, I'd take the busy part of the system and spread that out over a bunch of processors. But then they'd be talking to one another at every time step, and that would maximize maximize the amount of data that had to move. But if I put it all in one processor, there'd be no communication, but then that one processor would be the bottleneck. So load balancing has to be done dynamically in this case. You can't just sort of pre-assign everything to fix it at certain processors and then hope for the best. You might have to be dynamic about it. But let me go back and say how you could have a deadlock in this conservative case, and what's the algorithm to fix it. So to keep it really simple, let me suppose I just have 3 processors, and they're connected in a ring, and events can only go counterclockwise, following those arrows. So suppose that all the pawns are simulating, and they all get up to time t0, and they all know their neighbors are up to time t0. Nobody can go past time t0. Everybody's waiting for somebody else. So what do you do about that? That's a deadlock. If you've been waiting for a while, you send out a message to your neighbor, "Are you stuck too?" And if you get that message, you send it to your neighbors, "Are you stuck too?" And finally, if it comes around and you get your own message back, "Are you stuck too?" you know there's a loop. You know there's a deadlock. And then what you do is you send a new message saying, "All right, go ahead." And that goes around the loop, and everybody takes the next step, and hopefully that breaks the deadlock. Now, in this case where it goes around in a circle, that'd be a terrible bottleneck. You do it every time, but in more, let's say, generic kinds of simulations, that hopefully wouldn't happen very often. Okay, so that is how you deal with the dealing with deadlock. Okay, so that is the end of discrete simulations. Let me just summarize it all. So parallelism and locality arise naturally. We want to take advantage of that to make sure all the processors are busy and to minimize communication. And so in the discrete case, time is discrete, events are discrete. You're only talking to a finite number of neighbors at a time, and they're discrete time steps. And I need to get a transition function evaluated on all my neighbors and update myself. And so how do I assign work to processors? We call it domain decomposition. That's how I took the square and just divided it up into subsquares, because each domain was only had to talk within itself. And so I assigned that to individual processors. And in the regular case where I subsquares, it was easy. More generally, I have a graph. The graph represents who influences whom. And I represent the nodes as states, and the edges are dependencies, and I have to partition it. And that's called the graph partitioning problem, which we'll come back to later. Then I can either do it synchronously, where there's a global clock, or asynchronously, where I only change when the inputs change, and that can be either conservative or speculative. Okay, question. Is there a microphone for questions, or should I repeat the question? I'll repeat the question.
So for the asynchronous case, don't we also need a global timestamp so that different processors?
So for the asynchronous case, do I need a global timestamp? What I have is timestamps. And so, which everybody agrees on as to what that means. And so when you get a timestamp that comes in and let's say it's old, you have to back up to that particular timestamp. So the timestamp could be referring to something that everybody agrees on as a global value. Which could be, I did this at clock cycle, updated this clock cycle number 100, and everybody, and so you need some sort of agreement, or it could be some sort of real-time thing too. Does that answer your question?
Yes.
Okay, next question.
So piggybacking off that, so are you essentially choosing a clock to choose as your global sort of?
Right, so the question is, how do you choose the clock that makes sense in an asynchronous simulation? That's going to depend on the system that you're doing, and if it's a digital computer, there's sort of a natural choice. If it's a physical system where events are happening in a biological system, it would be real time, and your best guess at what real time is. Yeah, so it depends on what makes sense for your particular event-driven simulation. Great. Any other questions? So let's go on to particles. So a particle system, this is the next step of being continuous. I have a finite number of particles, so that much is discrete. They're all moving in space according to, say, Newton's laws, F equals ma. And the time is continuous, of course, and the positions can be continuous. And so stars moving around under the force of gravity, electron beams in semiconductor manufacturing where they're all being pushed around by electrostatic forces at slightly larger scale, you're doing molecular dynamics, which people do a lot of these days, and it's electrostatic forces pushing the atoms around. Neutrons get pushed around in a fission reactor, and there, when there's a collision, interesting things happen. You could have cars on a freeway, which have Newton's laws, plus you could have a model of the driver and the engine to sort of, say what the F is, and the F equals ma. And then there's balls in a pinball game. So, and you can make up many others. And of course, you can have a system which had both particles and a discrete event simulation. You could have a discrete event simulation of, say, the control system of your automatic driving car combined with the cars driving around. But I'm just going to talk about particles right now. So as long as nobody bounces into one another, as long as the forces are externally imposed, this is all embarrassingly parallel. The interesting part is computing the forces. And there are 3 different kinds of forces, and there's 3 different ways to parallelize them. So the force is going to be a sum of the external force, the force that only depends on your nearest neighbors in some sense, and then what I'll call the far field force, which could in principle depend on every other particle, like gravity. So external force, the simplest example would be fish are swimming around in the ocean, and there's an external current, and each that depends on where you are in the ocean, each fish just evaluates the function, what is the water velocity at my location. Everybody's independent and parallel, and the fish swim on. Also, if you have some sort of particle accelerator, or electron beam lithography device, you impose an external electric field, and each electron feels that. That's the dominant electric field, and it just evaluates it and decides where to go. So that's all embarrassingly parallel. The next more interesting one is when it only depends on your nearest neighbors. So that's why we have sharks are attracted to eat nearby fish. They only have to look at that subset of the data. When you have balls bouncing around, it's only when there's a collision. When they get really close, then you, of course, have a different law of physics. But here's an interesting one, van der Waals forces in fluids. So that's a model of how dipoles and multipoles attract and push away from one another. And it turns out it decreases like 1 over the distance to the 6th power. Gravity, remember, is 1 over r squared. This is 1 over r to the 6th. So it looks like it's a global force, but in fact, that goes down so fast that there's a cutoff. So it really only depends on the nearest neighbors. And one of the interesting things I think our colleague Bob Full did work on a few years ago is he thinks this is how gecko feet work. So when the gecko is walking on the ceiling without falling down, and can just stick and unstick its foot, it's about controlling the van der Waals forces. And so we will use some domain decomposition to make that all run fast. And then the one that requires the hardest math, and which has won many prizes, in fact, is the far field force. When everybody depends on everybody, the simplest example would be a 1 over r squared law for gravity or electrostatics. And but it turns out that any kind of force, as long as it gets smoother the farther away you are, and that's true of most forces in nature, and anything governed by an elliptic partial differential equation, if that's familiar terminology, you can use this trick to get the cost down from order n squared to order n. It all scales linearly. So, but we'll have a whole lecture on that later. That's a deep topic, but I just want to make you all aware of it today. But let's go back to the simplest case. And it's just 1 page, or a few lines of MATLAB to all the parallelisms expressed here in a data parallel way. This is the easiest way to write it down. So I'm going to have an array called fish P of all the initial fish positions. And this code actually works. You can think of it as just one complex number, the x coordinate and the y coordinate. So that's going to be the position I'm going to update. Then each fish has a velocity. And again, that's one complex number, which is a vector in 2D. Then I have an array of all the fish masses. And I want to simulate them starting at time t equals 0 up to some time t final. And the algorithm is going to be the simplest one possible. Every fish is going to move a very short time step in a straight line given its current velocity. That's called Euler's method. And I'll draw a picture of that later. Yes?
Sure, Professor. But I didn't caught up. But will there be some cases that the external forces interact with the elements? For example, using the current example in this case, won't the ocean current be fluctuated or disturbed by all the fishes
So the question is, what constitutes an external force that never changes versus one that depends on all the other fishes? So I would say that if the force depends on who's swimming around you, that's the second kind of force. That's the nearest neighbor force. And if it depends on the ones who are really far away, that's the far field force. So this only applies to the part of the force which is the truly externally imposed on you. And if there's a perturbation that depends on who's near you, that's the near field force. And that's going to be that's a different slide. Okay. Any other questions? So as I said, the algorithm is very simple. At each time step, I will simply ask each particle, how fast are you moving? And I will just move you in a straight line for a little bit, in the direction of the velocity that you're moving. So I'll loop over all the time steps, starting from time t equals 0, and I'll take little tiny time steps, dt, until I get up to the final time. Now, there's some communication here. It's not entirely embarrassingly parallel, and that's because I'm going to need to adjust the time step depending on how fast people are going. But the simple thing is I update the time step, I take my current position and just move it in a straight line in the direction of the velocity, times dt. I also need to update the acceleration, and so I'm just going to take, and that's the current in the water. That's a global function. All I need to know is where I am in the ocean. I evaluate the function which tells me the current, and so this is acceleration divided by mass, force divided by mass. That gives me the acceleration. And then I do the same, straight line update. I take the velocity and move it a little bit in the direction of the acceleration to get the new fish velocity. And so that updates me from time step to time step. And if I didn't need to ever change the time step, that's all the code would do. But I'm going to update the time step because if the time step is too small, I'm going to be very inefficient. And if the time step is too big, I'm going to get the wrong answer, right? So how do I choose a decent time step? The rules are kind of complicated in real applied math, but here's a simple way to capture it. What I'm going to do is make sure that every particle, every fish, just moves far enough that that it doesn't go too far. So what I'm going to do is I'm going to take the velocity divided by the acceleration. That would be how far it would move, and multiply by 0.1. So this tells me I'm not going to change anybody's position by more than 10%, right? So I'm not going to take a huge step. Everybody's going to move at most 10% away from where they are now. And so to do that, I need to know the largest velocity of anybody, the largest acceleration, and then I do this kind of scaling. So computing the max, that's the communication. That's a global reduction for which, I think in the tricks with trees, you saw that's a nice binary tree that is all done very quickly. And so you might do this every time step, or you might say it's too expensive and only do it every 10 time steps or 100 time steps. That's a tuning parameter when you write your code. Okay, so that's external forces. These are the simplest by far, and we call it embarrassingly parallel, or map reduce, which by analogy to that old name that was invented at Google. So the map is where you apply a function independently to a whole bunch of processors. Nobody depends on anybody else, and the reduce is where you compute a max or a min or some other function of some of the data, and so this is very straightforward. So the next step, where it gets interesting, is where the force depends only on your nearest neighbors. So now we have to do a little bit more. And in fact, I think your homework is related to this. So the simplest example would be collisions, where you bump into one another in your billiard balls. So what's the simplest way you could imagine doing it? You look at every pair of particles and you ask, are you close enough together, and bounce. And in that case, that would be, if you look at every pair, that's order n squared. And that's expensive, and so we want to do it more cheaply. And so we're going to use that same trick we did before, which is domain decomposition, to get the cost down from order n squared to hopefully more like order n. So suppose all of my particles are living in some nice simple square domain like that, and I have 25 processors, which I've arranged here in this 5x5 grid. I'm going to assign each processor the particles in its physical domain that corresponds to its subsquare of the domain. And so that's naturally called domain decomposition. And if I have n particles and p processors and everything's evenly distributed, I'll just make that simplifying assumption for a moment and fix it later, then everybody's going to have about n over p particles to be in charge of. So the question is, if this is the assignment of particles to processors, how do I take a time step? How do I compute a force? Because somebody might, like this particle, might collide with that neighbor there who's owned by somebody else. So that's what I have to watch out for. This guy is so far away from the border, I don't have to worry about that. So here's the idea. I just need to understand the interactions of particles that are near the boundaries. So it's that surface to volume effect that we had before. So for each domain that's assigned to a processor, I'll look at the border region. Sometimes that's called a ghost zone or a halo. That's different words in the literature, but the particles near the border. And if you're not near the border, you're not going to move very far, so I know you're not going to collide. So most of the particles are going to be in the inside, in the white parts, and I can just independently in parallel move them and not worry about collisions. The only communication is when somebody's in a blue zone, I have to transmit that person's position and velocity, whatever else is relevant to the nearest neighbors, and then these two processors will realize, oh, there's going to be a collision. And there, that interaction will take place, but that's only going to be done for a small fraction of the particles, the ones in the border, and that's a lower order term, in the total cost for the same reason that we did domain decomposition before when we were doing sharks and fish. So that's a perfectly natural thing to do when the particles are uniformly distributed, but that's not always the case. So what do you do when the particles are all clustered? I'm still going to use domain decomposition, but now I'm going to use different shaped domains. I'm going to have to divide space up in an uneven fashion. And the standard trick that people have used for this is something that's called quad trees in 2 dimensions and oct trees in 3 dimensions. I'll just draw the 2-dimensional case. So what is a quad tree? At the top level, you divide space into 4 boxes. You look at each box and say, do you have enough particles inside that it's worth dividing you again? Here, there are only 2, I stop. So here, I look inside that square and say, I better divide it into 4 more boxes again. That one doesn't have anybody in it, I can quit. Those are fine, that box has to keep going. So you can call this a quad tree because there is one node that represents the entire square. Then it has 4 subnodes corresponding to these 4 subsquares. So that's one tree with 4 children. Then these don't have any more children. This node has 4 more children, so it's a quad tree. And you keep on dividing and conquering until everybody has, let's say, 1, 2, or 3 particles inside of it. Depending on how you want to do how many processors you have and how many particles you have. So the idea is that at this point, use the same trick as before. You only communicate the particles near the boundaries with your neighbors, but obviously the particles are moving, so you might have to. So what happens if a particle moves from this box to that box? Well, just move them and let the next processor be in charge. After a while, you might have to rebuild this tree and rebalance everything. But as long as everybody's moving at a not too high rate of speed, you can leave this in place and it'll stay reasonably load balanced for a number of iterations, and only once in a while do you need to rebalance. Okay. So now let's go to the interesting case, which is far field, where everybody depends on everybody else. And let me give you what seems like a very simple example, which actually has a surprise in it too. So let's suppose everybody depends on everybody in some non-trivial way that you can't really simplify very well. So, but the simplest algorithm means that everybody has to interact with everybody else. You have to do n squared work. So here's the simplest way you could imagine doing it. Suppose I have 5 processors. Each one is going to get n over 5 particles.